Welcome to the computer science series of artificial intelligence. As a continuation of last module where we did the different informed search techniques, this is a continuation of that, and in this module we will see about hill climbing algorithm. And before we move on to the actual module, this is the question from the last phase where we asked to solve. So, here is the question: we are helping a small delivery robot to find the shortest path from W to H, and the robot has to navigate through the city. Assume that the nodes are the city, and you are given different cost, the actual cost as well as the heuristic cost. Heuristic cost are at the right side and the actual cost are there. So, we will just see how greedy and A star would help. Suppose we have greedy, and for greedy it is only the heuristic value h of n. We start at W, and with W the heuristic value for W is 7. So, I am just putting as 7, and there are two paths here, one is A and another one is B. A's heuristic value is 6 and B's heuristic value is 5. I am putting 6 and 5. The minimum value is B. Remember, we said it is going to be a priority queue, and in that queue it will choose the minimum value of the list where we have A and B, choosing one which is B having the minimum value of 5. Again, branch from B there is only one branch which is D with a value of 3, and from D there is no other path. So, it will stop here. So, the greedy best first will not work for this algorithm. So, for this particular problem, greedy will not work. Now, let us come to A star. So, the conclusion for greedy is greedy does not work. Greedy will not work for this problem because it will stop at D. For A star, from W we have A and B, the actual cost is 2, and from W to B the actual cost is 4. From A the heuristic value is 6, and for B the heuristic value, I am putting in brackets here, it is 5. Now, the total cost for A star, remember for A star it is f of n is equal to g of n plus h of n value. So, if we add 6 plus 2, it is going to be 8, f of A is equal to 8, and for B it is f of A is 5 plus 4 equal to 9. So, this is minimum, it will take A, and from A it will go to C and D. The cost here is 3 and 6. The total cost of G 3 plus 2, it is going to be 5 plus C's value is 5. Here it is going to be 10. For D it is 3. G of n value is 2 plus 6, 8 plus 3 equal to 11. So, we have 10, 11 and 9. Remember, again it is a queue, and in the queue we have 9, 11 and 10. This is minimum. So, it will branch out B. From B it is going to be D, and D the value, the heuristic value is 3. So, 4, and from here it is going to be 2, 4 plus 2 plus 3, 9. Again this is minimum, but there is nothing here. So, again it will go back and it will take the C, and from C it is 4, and it will lead to the goal, and the goal's value is 2 plus 3 plus 4 plus 0, because heuristic value of h is 0. This is heuristic value and this is g of h value. So, the total cost is going to be 9, and if you see the path of A star, it is W, A, then it went to D, again it goes back to C and H. So, this is the path for A star, and the cost is going to be 9, which is optimal. So, this is the solution for last class. Now coming to today's session, we are going to do on hill climbing algorithm, and it is typically like how we climb a simple hill, and we call it as an optimization algorithm. The word optimization is, okay, we get the result and it may not be the best result or the worst result, okay, it is an optimized one and we are happy with that kind of a result. That is the optimization is all about. And here we are going to find what about the local minima or maxima in a particular space, search space. A search space would be something like a big tree, very similar to what we have done in the searches. We have n value, we call this as n, and is an iterative improvement algorithm. I will just explain this. Suppose this is an graph, assume that this is a state space, x axis the state space and y axis we have the different heuristic function, and by some means we get measures like this. This assumes like a hill, and remember, in a hill we always tend to, suppose we want to climb a hill, starting from here we will look at the next direction, the next path it is to be moving up, again moving up, again moving up. The same process is being conducted in this hill climbing algorithm also. So assume this is some kind of a figure we get out of the manipulation between state space and the heuristic value. Now following things can occur. One, it can come at this point, it can grow until this point and come back here, and this is called as a local maximum, meaning when we are at this point we are thinking, okay, this is the highest peak, we are not sure this is the highest peak, but we know that this is only the highest and then tend to come back. So this is the, we call it as local maximum. This may be hidden from our view when we are right here, so that is going to be local maximum. Now at this point is actually the global maximum, this is actually the point that we want. And sometimes when we go down, there are some points where it is lying flat, this is called as a flat region or a plateau, very similar to the hilly conditions. And when it comes down, at this point is called as a local minimum, whereas the global minimum is coming at this point. So our answer may either be here, here, here or here. The actual answer may be here or here, but we may tend to look this as an answer or this as an answer. Why? Because we are looking only at the immediate neighbors. We are not looking at what is in future, but in the hill climbing algorithm, the most important one is immediate neighbor that we will look at. And based on the immediate neighbor, we will analyze whether to go to the next point or not. So this is the intuition behind hill climbing algorithm. We will look at a few examples here. So how it normally works, this is the same diagram that was that earlier. How it works, we start with the initial solution, let's say our initial point is somewhere here. Then we will evaluate it, what is the point, and then we will see what is the next neighboring solution is and evaluate those neighbors, and if the neighbor is better than, suppose I call the current one as A and the next one as B, if B is better than A, then make B as a current point. Our current point is B, and do the same step. So check the neighbor, if it is better than the previous one, go, otherwise remain the same. So it goes and finds that, okay, this is going to be the global local maximum. So that's what the fifth point is given. Move to the best neighbor if it's better than the current solution. or repeat 3 to 5, generate neighboring solution, evaluate and again move back. So, this is the example, the first example that we do is to find the maximum value of minus x squared plus 5x plus 10, and this all of you might have done in 11th or 12th standard. So, how do we do it? First we will address it mathematically, and the same problem we will also go through how it is done using a hill climbing algorithm. So, let us take this algorithm. Suppose f of x is given as minus x squared plus 5x plus 10. To find the maximum value, we take the differentiation of it. Dy by dx is equal to minus 2x plus 5 equal to 0. So, x we will get as 2.5. And d squared y by dx squared, it will be minus 2. Therefore, we can say x is going to be x, if we substitute, if x is substituted, we get maximum value. We get maximum value here. Now, if we substitute f of 2.5 plus 5 into 2.5 plus 10, if we substitute this one, substitute 2.5 in equation 1, we get, you can calculate and see that it would be 16.25. This is the maximum value that we are going to get it. This is a mathematical way of finding out 16.25. Now, for the same problem, we will do using hill climbing algorithm. So, this is a typical algorithm, that is a Python program to find the same equation. Okay. Here, if you see the first two lines, this line, this is going to be the equation, mathematical equation. So, what it does is, this is the x value, and what is it returning is the f of x value. This line is f of x. Now, we are going to use the hill climbing in order to generate the maximum value. Let us see how it works. See, here we are going to do 1000 iterations in a step size of 0.1, okay, and we are going to start. So, this is the x value, the current x value from minus 10 to 10. So, x value we are going to take it as, I will give the result also. After executing the program with the plot, it will have the result. The result would be from minus 10 to 10, and from minus 10 to 10, we take the current value. Current value is f of x. This is the from the objective function that we calculated right here. So, we take a random point, calculate f of x and store the path. The path is x comma, this is a tuple, this value is a tuple. So, this path will contain the value of x comma y, some value of x comma y, or f x comma this f, suppose I assume f of x is equal to y. Okay. So, this x comma y, it will store as a tuple. Now, along with this, we are going to start the iteration. We are going to see the calculation of the neighbor. Okay. So, how is neighbor calculated? Neighbor is the current x which is at this point. This current x plus some random value we are going to calculate. So, suppose we are at this random point here, okay, and current x plus some step size value we will get at this point. Maybe some, if I start around at this point, minus 1.6, and the next point would be minus 1.62. Okay. So, in the step size, that is 1.62 is the x value, and from x value we are going to calculate the f of x value at this line. Neighbor value is this. So, we have x value as 1.62, and this is going to be this line. So, we will calculate. Now, we know what is neighbor value and the current value. So, if neighbor value is, this is why, if neighbor value is greater than the current value, then use the current value as the neighbor value, make this as a current point and grow up. So, current value is neighbor value and append the path. The earlier path you have only x, y. Now, you add this path also 16.2 and the value that comes here. So, you will have one more. So, do this until 1000 times so that we would know at which point is reaching the maximum, until 1000 points. See, when it will stop either at 1000 iterations or when there is this does not obey, when neighbor value is not greater than current value, this will stop. It will happen at this point. Neighbor value would be less than this point here. At this point it will stop and it will say, okay, we have got the local maximum at 16.25. This value is 16.25. So, this is an example that we are doing with hill climbing algorithm. The second example is from our AI itself, which we have seen before. It is called as an 8 puzzle, where we have seen earlier. Okay, this is an 8 puzzle problem. The idea is here you would see the numbers in a tile, the 8 numbers in a tile. We have to put it in order. Actually, the numbers should be something like, this is the goal that should be we should have 1, 2, 3. This is the goal that we want. But initially we have, this is the goal. Right now we have at the initial stage. If you see, 1 is at the correct position, 4 is not at the correct position, 2 is at the correct position, 3 is not at the correct position, 4 it is not correct position, 5, 6, 7 and 8, all of them are in the correct position. So, the heuristic value is number of misplaced tiles or the Manhattan distance. Okay. If you see, the number of misplaced tiles is 1, 2 and 3. Either one of it we can take. Here we are taking the number of misplaced tiles. So, 1, 2 and 3. So, the heuristic value is 3. Now, from here there are 3 possibilities that we can go. Either it can, if this 1 we can push it down, which will lead to this path, or 3 can move left, that will lead here, or 6 can go up. I have marked it as up. This is marked in this direction here. So, while we calculate the heuristic value for each of it, you could see that heuristic value here is going to be 4. The reason is, apart from the 3 that we had, this is going to be wrong. This portion is wrong. So, we have 4. But here the heuristic value is reduced because 3 has come to the original position. Remember the heuristic value, say the goal value, I would write it as 1, 2. This is the original portion that we actually want. Whatever I write in red is visible. This is the goal position. So, goal I have written in red, and this is actually what we want. Now, from the trial, if we move the first instance, if we move this 3 to the left, we will get the heuristic value of 2, while others, here the heuristic value is 4 and here it is 4. So, at the initial start, so assuming that we are having the hill climbing, heuristic is equal to 3. Now, if you want to get down, so here it is going to be monotonically decreasing. Here we want in this part, now suppose we have the goal which says 1, 2, 3, 4, 5, 6, 7, 8. Here the heuristic value is 0. So, we want the heuristic value to be reduced from 3 to 0. This is our goal. Now, from 3 we have 2 other heuristic value, 4, 4, and the third heuristic value which is less is 2. So, hill climbing will choose only this because from here this neighbor is better. So, comparing this, we will move to the next one, where the heuristic value here, the goal is to have h is equal to 0. So, from 3 we move to 2, and from 2 we have other 3 heuristic value. So, if we look at this level, from this 3 it can either move to this position, which is here, this is right, and 4 can come down, this is down, and yeah, from here 3 can move towards right, and this 5 can move towards left. Okay, you can see the difference, and you can calculate all of these, and once you can manipulate these positions such that when at this stage all the h value here and here are 3, and here also it is 3, but at this position h is equal to 1, okay, because we want it is going to be in the reducing side. So, we have h is equal to 3, we will choose the next neighbor better move, which is h is equal to 2, then the next better move as h is equal to 1, and once we are here, the other move is going to be h is equal to 0, where we will be moving the exact same position, say from here to here. This is the solution of hill climbing, and if you draw the graph, okay, so you have n as the search space, we have 3, 2, 1 and 0. So, it is going to be, the algorithm is going to be monotonically decreasing. Okay. Either it has to be monotonically decreasing or increasing. So, we have gone at the lowest level and we have got the answer. Now, hill climbing will not work in some cases. So, this is again the similar example where the hill climbing will not work. Take for instance at this point, here h is equal to 12. Now, when we move up or down, the hill climbing here it is going to be 13 and 11. So, you take this path, this is minimum, and from 11 you again get 12, 12 and 12. And if you see from 12 and 11 and again 12, we are stuck at a local maximum here, because 12, 11 and 12, this is 11 and this is 12 and this is 12, we are stuck here. Okay, we got a local maximum and this is not the answer. So, hill climbing may not work in other directions. Okay. So, again, what are the advantages and disadvantages of this method? The advantages is going to be very simple to implement, and it works for many different problems, and it requires only very less memory, and you saw the code that we had. Okay, it is just a comparison between the two immediate points. So, in that case we need not we actually do not want enough memory. So, only the neighboring points need to be saved. So, we can find the solutions very quickly with the hill climbing algorithm. Now, what are the limitations? There are more limitations here. It can get stuck in local optima. Like for example, we did that example, the 8 puzzle, where we could not find the original answer. The heuristic value we want is actually 0, but it may get stuck. The same case can be extended to other problems also. So, it is not guaranteed to find the optimal value of the global optimum, and it depends on the initial solution that we have. And some in a complex landscape, which we gave at the beginning of the session, with different landscape. A landscape is just a search space with n value where we had something like this. If this is a complex landscape, hill climbing may not work. Now, there are some other variants of hill climbing where people have done some research in order to give the correct value. So, those are going to be stochastic hill climbing, second one is steepest ascent, third is random restart, and fourth is simulated annealing. I will just give a brief overview on each of it. In the stochastic hill climbing, instead of choosing the best neighbor, it is the second step that we did. Whenever we choose the value, we said, okay, what if the neighbor is better than the previous step, we will select it. Now, instead of selecting the best neighbor, it randomly selects a neighbor, and based on the random measure, it will have a probability of selecting the neighbor, and that is proportional to the improvement of the problem. And the advantage here is it can escape local maxima or local minima, and it can also traverse the flattened space. If it does not improve the current state, it will take the move as the earlier state, and in essence what it would do is it would traverse the entire flat space in order to achieve the global optimum. In the second method, which is steepest hill climbing, it is the first state is the same, where we are going to have the initial random state. Now, instead of selecting the random or the next best value, we are going to have the highest value in the steepest ascent, and other than that it is all the same. In the third method, the random restart hill climbing, instead of one process, we are going to have a number of restarts, number of starting techniques, and we are going to use the steepest ascent each time of the each time for the hill climbing method. And suppose we have 5 times restarting, we will get 5 different local optimum answers, and out of these 5 local optimum answers, we will choose the best optimum solution. So, the idea here is for fixed number of techniques or restarts, we will use the steepest ascent and compare the local optimum from all the restarts and get the better option. The last method is the simulated annealing. Here it is based on the physical process of annealing, where metal is heated to a specific temperature and slowly cooled down. The algorithm is shown here, where the initial state is the same value and same thing that we did before, except that we have 2 parameters, one is T, another one is delta E. T is the maximum temperature, but this can be a parameter in our case, and delta E, it is the neighbor conditions, and based on these two with the probability measure, we will compare and see that the optimal solution is achieved. And this algorithm, this is just an overview. In the next class, we will do in detail about this algorithm with an example. Coming to the summary of this session, in this session we saw a local search algorithm of hill climbing. Why is it called local search? Is because it looks at the immediate neighbors only, not at the far end. And it is although simple, it cannot work on all problems, and we have different variations of the hill climbing. And in the next session, we would get started with the simulated annealing, a genetic algorithm, and the adversarial search.